Hello everyone, and welcome to Session 2 of our Marionette Monday webinars. My name is Sarah Barrett, and I am an Architect Product Specialist here at Vectorworks. I will be leading you through our intermediate level session, Marionette Webinar 2, The Power of Lists. Today we are going to talk about the power of lists. Lists are essential to creating complex designs, and we will go over how Marionette handles lists, how they are created, sorted, and parsed. We will also learn some other aspects of Marionette, like wrapping networks and creating parametric objects. Last webinar, when we were going through nodes and networks, I was saying what the output values were for each node, but when lists and mathematical operations are used, the output values of nodes can become very complex. As this happens, it can get much harder to figure out what the output values will be without seeing them. Not only can values become complex, but also errors can happen that need to be found and corrected. This is what debug mode is for. When you click on debug mode in the Marionette toolbar, the resource selector can no longer be used, and a pointing hand icon replaces the typical cursor. If you move the hand icon to hover over a wire within a definition, the wire highlights red. When you click on a highlighted wire, a dialog box appears showing the values that are flowing through that wire. If the information flowing through that wire is data, you will see number or string values. If the information is geometry, you will see Vectorworks handle type, colon, and then a number. This is how Vectorworks categorizes different objects. Vectorworks and Marionette refer to objects in scripts as handles. Each object has a corresponding integer and name that can be used in Marionette definitions. To find a list of these types, you can go to the appendix on the webpage developer.vectorworks.net. As you can see, the middle column gives the integer for the type, and the right column gives the string name for the type. So in Marionette, the output of an extrude node is Vectorworks handle type colon 24, because as you can see in the list, 24 is the integer for an extrusion. If you want to know the data coming from a node when no wire is coming from its output, you can use a dummy node. A dummy node can be found in the debug folder. When you connect it to the last node in your network, you can then click on that wire in debug mode to see the information. The dummy node has no effect on your network other than to create a wire to use for debugging. If you click on a highlighted wire and an error message pops up instead of a value list, that means that there is an error in the node in front of that wire or in a node further up the definition. The node must be identified and fixed before the wire can display data. Sometimes when an error message pops up, there is a button that selects the problem node for you. If the error message does not include a button like this, then following the errors in the wires backwards can work, just like when you are trying to find the problem bulb in a string of lights, and changing that bulb will turn on all of the lights behind it. So for the sake of error checking, let's create an error in our network. Let's change the value of the sphere's radius to 0. We know that a sphere can never have a radius that equals 0, so the definition will not be able to create a sphere, and therefore all of the other aspects of the definition that depend on that sphere being created will not work. Now let's run our definition and see what happens. We get an error message, and it points us to a particular node, the contour node. This is the node that is causing the definition to throw out an error. So one of the inputs of this node is somehow unworkable. An input could have an error, or an input could be in an improper format for the node it is flowing into. If an input has an error and the wire is clicked on while in debug mode, it will not produce a value list. If the input is in an improper format, however, a value list could pop up. We will just have to do some searching to figure it out. When we click on the wire going into the dir input, we see a value list first, and then the error message. This means that the wire is producing a value, but the overall network is still pushing out an error. This is true for the point input and the delta input. If we click on the wire going into the Object 3D input, we don't get a value list, just the error. So if we follow that wire backward, we get to the sphere node. Now we can check the inputs of the sphere node, just like we did the contour node. We see that clicking on the input wires gives us value lists for each, so one of those values must be somehow unfeasible for the sphere node. In this instance, there is another way to discover the error in the script. If you look at the outputs of each of the nodes, you see a number. This represents the number of values coming from the output of the node. A 0 value almost always indicates an error in the network, unless it is with something like a filter node that has an either-or functionality. Without clicking on the wires, we could have followed the issue back to the source by locating the 0 output values. Debugging is a term that comes from scripting, and it is simply a synonym for testing. There are several terms and concepts from scripting that we use in Marionette on a regular basis. All of these terms have to do with data, and learning these is the first step in understanding the difference between traditional modeling and algorithmic design. A list is the form that information takes when it passes through your algorithm. Even if there is only one value, it is essentially a list of one. In scripting, a list is written by putting a bracket at the beginning and end and separating each value with a comma. A list of numbers looks like this. Another way to write a list is to put a new value on every line. This is how lists are written in the dialog windows that pop up when debugging a wire. They look like this. The bracketed numbers on the left are index numbers. Index numbers represent the position of an item in a list. In Marionette, every list starts with an index of 0. In other words, the first value in a list has an index of 0, the second has an index of 1, the third has an index of 2, and so on. Index numbers are a way of standardizing your data, just like a filing system. A range is a series of values that go from smallest to largest and have an equal step in between them. 1, 2, 3, 4 is a range. 1, 2, 4, 5 is not, because the steps between them are not equal values. A range is a fast and powerful way to make lists. There are 3 nodes that can create a range in Marionette: range, sequence, and series. All 3 start with the same parameter, the starting value of the range. Then each uses 2 different variables to create a range. Each can give you the same result, but they use different parameters. For example, if we want to create the range 0, 3, 6, 9, 12, 15, 18, we could do it in 3 different ways. With the range node, we would input the first value, 0, the last value, 18, and the number of steps, 6. The number of steps means the number of transitions between values, not the number of values themselves. If you look at the list as it is written here, the number of steps would equal the number of commas. The next option would be the sequence node. With the sequence node, we would input the first value, 0, the last value, 18, and the value of the step, 3. The third option would be the series node. With the series node, we would input the first value, 0, the value of the step, 3, and the number of values, 7. There are 5 primitive data types that we use in Marionette. Some of them are standard mathematical terms, but some are specific to programming and scripting. Any raw data that is input into Marionette must be in one of these 5 forms. The first one we are going to talk about is Boolean. Boolean is a choice between true or false. You can almost think of a Boolean as a light switch or a toggle. It has only 2 options. true or false, on or off, left or right, in or out, yes or no. You use a Boolean in a network when you want to set up an either-or situation. There are two types of numbers used in Marionette: integers and real numbers. Integers are whole numbers. They are used to represent a position or an entity. Therefore, they can never be fractional. In Marionette, an integer would never need a unit because it is not used to describe size or distance or volume. That is a real number. Real numbers can be whole or fractional because they represent values. The int node in the input folder supplies an integer, and the int node in the math folder converts a real number to an integer. The dim and real nodes in the input folder both supply real numbers. The difference is dim nodes can supply units that are independent of document units. The float node in the math folder converts integers or strings into real numbers. Floating number is another term for real number that is often used in scripting. A string is a value that is not a number. It is a letter or a symbol that represents a name or a variable. When you name something in Marionette, that name is a string, even if it has numbers in it. There are three nodes in the input folder that require strings: the name node, the string node, and the objects by criteria node. The objects by criteria node uses a string to reference a certain category of object. If you want to select objects by type, such as line, polygon, or rectangle, the string always begins with t equals, and then the string value for that object type. If we go back to the appendix image, we can see that the string value for a rectangle is rect. So to reference all rectangles in a file, you type t equals rect in the object by criteria node. Points and vectors are coordinates that describe a position in space or a direction. They are made up of real values, and they look like this. They are not necessarily lists. Because they are within parentheses, they are usually treated as a single object. Vectors are written the same way as points, but they do not have units because they represent a direction and not a position in space. Understanding value types is important for creating a working definition. In this network, there is an input value that is described incorrectly. Let's debug the network in order to find it. So first, let's select the debug mode in the Marionette toolbar and then click on any wire. An error message pops up that says type error, which means that one of the values is in the improper format, as well as float object cannot be interpreted as an integer. This means that one of the values in the definition is a float or real number when it should be an integer. If we look at our definition, we see that we have 5 real input nodes, so it is possible that one of those should be an integer node. We also see that each of these node outputs is going into a series node. If we remember from a short while ago, a series node takes the first value of a list of numbers, the step value of a list of numbers, and the number of values of a list of numbers. The first 2 inputs are either direct values or measurements within that list, so they are real numbers. The third input cannot be a real number because it is a count and it can't be fractional. You can't say that there are 2.6 values in a list. It's either 2 values or 3 values. So the input type for the count input on a series node must be an integer. So let's get an integer node from the resource selector. Copy the value from the real node, paste it into the integer node, disconnect the real node, connect the integer node, and rerun the network. And now our network works as it should. If you remember from the last webinar, the three types of nodes that deal solely with data are the data flow nodes, the math nodes, and the point nodes. As you can see in this definition, there are a few point nodes, a single object creation node, and the rest are data flow, math, and point nodes. Although there is only one object creation node, this definition is creating many rectangles, as we can see here. This network creates 100 rectangles that are offset from a square grid by a random value between 0.1 and 1 in both the x and y direction. The first section of the network is creating a list of 200 random numbers between 0.1 and 1. It does this by repeating the high and low limits 200 times and sending those to the random node. It then unzips the list into two, first one value in one and then the next value in another, until there are two lists of 100. The next part of the definition creates a series of 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, as you can see by looking at the inputs of the series node, where the step equals 1 and the count equals 10. It then cross-references them using a mix2 node to create two lists of the 100 possible combinations between two copies of the same list. If you remember from the last webinar, this is how we create a point grid. The third part of this definition adds the two sets of random numbers to each set of the cross-reference series, then converts these into x and y values to be used as origin points for 100 rectangles. When there are multiple inputs on a node and one of the inputs is a list longer than the others, the shorter lists are repeated until the list lengths match. For the rectangle node, there is one default width and one default height, and it is repeated over and over for every origin point that is sent into the node. This is what the result of this definition looks like. Now say we wanted to remove the random aspect of this definition. All we would have to do is disconnect the random values from the add nodes. If they are not connected, the add nodes will use the default value for A in the add node, which is 0. When we remove these random values from this definition, you can see the rectangles are in a perfect grid. Data flow nodes can not only create lists of data, but they can also sort and organize data. In this example, we have these rectangles that are all different sizes, and we want to identify the smallest and largest rectangle by area. First, we have to tie these rectangles to our Marionette definition, and the easiest way to attach several objects is to group them and name that group. So I select all the rectangles in the drawing space, and I go to Modify, Group, and then in the OIP, I name it Rectangle Group. We then place a name node in the drawing and copy the name Rectangle Group in the OIP. We can name the node Rectangles for clarity. We can then attach a Contents node to that name node. A Contents node is in the Operations folder, and it returns the objects inside a container without actually removing them from that container. In this case, our container is a group. Now that we have a node output that is a list of rectangles, we need to find out their area. We do this with a getArea node. Now we have an area for each rectangle, and we know that this list of area values corresponds to the list of rectangles. So if we want to extract a particular value from the area list, we know it will have the same index number as the corresponding rectangle in the list. So the greatest area value in the list will correspond to the largest rectangle. To find it, we will use a max item node. Let's place a max item node from the data flow folder into the drawing. With this maximum value, we want to go back to our area list and find the index number for that area value. And we can do that with an index node from the data flow folder. Since that index number will be the same index number of the rectangle we want, we use that index number to retrieve that rectangle from the original list, and we do that with a getItem node. Once we have that item, we can attach an attributes node to highlight it in our group. When you use an attributes node, whatever you set the attributes of the node to be, apart from attributes by class, those are the attributes that will be given to the object that passes through the node. Now we can follow the same procedure to find the smallest rectangle. We simply exchange the max item node for the min item node. So we can copy that section of the definition by selecting and dragging while holding down the Option key. The plus symbol indicates that I am dragging a copy of the nodes, not the nodes themselves. Now let's get a min item node from the resource selector and connect all our nodes. Now let's change the second attributes node to a different color. Let's run our network to see the result. Now let's array our rectangles from smallest to largest with an even distance between each. First, we don't want to change the original group of rectangles, so we make a copy of the group within our definition. I've already done this to save us some time. This time, we don't want to use the contents node because that allows the editing of objects without removing them from their container. For this exercise, we want to remove the rectangles from the container so that we can array them. So instead of a contents node, we will use an ungroup node, which is also found in the operations folder. We'll use a getArea node again, but this time we don't want a particular area value. We want to sort the area values instead. So we use a sort node from the data flow folder. This node always sorts number values from smallest to largest, and it sorts string values alphabetically. Once we sort the list, we use an index node again to get the corresponding index numbers from the original list that match the sorted list. Then, with these indices, we can apply this sorting to the rectangles with a getItem node. Now we want a list of points to array our rectangles on. First, we get a getWidth node, which will give us the width of each rectangle. We want to make sure that our rectangles do not overlap, so we will use the width of the largest rectangle as the step in our range of points. So we will need a max item node again. We also need a point for every rectangle, so that means the count of our range will be the same as the count of rectangles. We can get this number with the getListLength node. Since we have a step and a count to make our range, we want to use a series node. We don't need a value for our start input because the default start value for the series node is 0. Some nodes give the default values of the inputs in their descriptions, and others can be seen by double-clicking on the node and reading the script inside. Now, with the output of the series node, we can create 2D points with these values as x values. Let's give these points a y value of 18 so that our array is closer to the definition in the drawing space. As I mentioned before, if there is a different length of values in two different inputs, the inputs with shorter lists will have their last value repeated until the list lengths of all the inputs match. So even though we were only giving one value to the y input of this point2D node, this y value is automatically repeated for every x value that passes through the node. Now we need to move our rectangles from where they are in the group to our series of points. We can do this with the getRectangle and setRectangle nodes. We simply take the list of rectangles from the getItem node and apply it to the getRectangle node. We apply those widths and heights to the setRectangle node, as well as the list from the getItem node to the rectangle input of the setRectangle node. And then we apply our 2D point to the origin input of the setRectangle node. So with this method, we don't need to know where the rectangles were originally. We don't move them from one place to another. Instead, we override their data and give them the origin point we want. Now we have arrayed our group of rectangles horizontally. As you may have noticed, in this definition there is a wrapper node. A wrapper node is a node you create by wrapping a Marionette network into a neat, manageable package. When I double-click on this wrapper node, I can see there is a network of nodes inside. As we are making these definitions, they can begin to look pretty messy. If you create a network that looks like this, and you come back to it the next day, it can look completely incomprehensible. And if you're trying to share your definition with someone else, you can imagine what his or her reaction would be. Also, there are often certain patterns of nodes that you find you use very often, and it would be a huge time saver to be able to package them up and use them over and over again. This can be done with wrappers. A wrapper is a Marionette network that has been packaged up into a single node. All you have to do to create a wrapper is right-click on any node in the network and select Wrap Marionette Network. If you double-click on the wrapper, it takes you inside and shows you the full definition. The orange border around the drawing space tells you that you are inside a container, just like a group or a symbol in Vectorworks. When you are inside the wrapper, you can edit the network just as you would normally do. A wrapper takes the attributes of whatever class is active when it is created. The wrapper for this network is solid white because the None class is my active class. But if I change it to one of the Marionette classes and I wrap the node again, it takes the attributes of that class. I can also change the class of the wrapper by simply going to the OIP and choosing a new class from the drop-down menu. We can also name a wrapper just as we name any other node. As you can see, its default name is set to wrapper, but you can change it to whatever you like. So let's change it to My Network. When we look at this wrapper node, we see that there are no inputs or outputs. It functions solely as a container. But say we want to incorporate this package network into a larger Marionette network, so we need to give it ports. The way to give a wrapper ports is simply to name the nodes that you want to be exposed on the outside of the wrapper. If a node has an input or output port unattached and you name it, that exposed port will show up on the outside of the wrapper node. If I name an input node, the information in the OIP of that node will now show up in the OIP of the wrapper. If I double-click on the wrapper and I give these attributes nodes names, they will show up on the outside of the wrapper. So let's name some nodes. This attributes node is setting the color of the largest rectangle, so let's name it largest. This attributes node is setting the color of the median size rectangle, so let's name it median. This attributes node is setting the color of the smallest rectangle, so let's name it smallest. And this attributes node is setting the color of the average rectangle, so let's name it average. We also want to expose the info from the OIP of the name node on the wrapper, so let's name the name node group. Now, when we exit out of the wrapper, we see our 4 output ports corresponding to the 4 attributes nodes that we named, as well as the information from the name node in the OIP. But maybe I only want to wrap parts of this network. I may use this network again, but I also may want to use different parts of it in other networks. To wrap part of a network, disconnect that section from the network, name its inputs, outputs, wrap it, and reconnect it. So let's wrap the section of the network that sets the attributes of the largest rectangle. These nodes are used exclusively for this section of the network, but the getArea node and the contents node are not, so there are 2 approaches to incorporating them into the wrapper. The first, which we will do with the getArea node, is to copy the node and use it inside the network. So let's copy the getArea node and connect that copy to the same places that the original is connected, and then disconnect the original. The second approach, which we will use with the contents node, is to add a pass node to the definition. Instead of copying the contents node, let's place a pass node in the drawing. A pass node does nothing to the information that passes through it. It simply adds an apparatus for creating an input or output port for a wrapper. Let's connect the pass node to the input ports that the contents node is connected to, then disconnect the contents node. When I am naming nodes to be used as wrapper ports, I typically have the name match the input or output port of the node itself, or match the name of the output port that will be attached to it. In this case, let's name it OBJS, which is the name of the contents node's output port. Now we have a mini network that we can wrap. I've already taken the liberty of wrapping the network into more comprehensible parts. As you can see, we have 7 wrappers in this network. If I still wanted this network to be one wrapper though, I can simply wrap it again. You can have wrappers, inside wrappers, etc. If we double-click on them, we can see which part of the definition they represent. This first wrapper is similar to the one we just created, getLargestObject. The next is getMedianObject. As you can see, it incorporates that section of the definition. The next is getSmallestObject. And the next is getToDCenterPoint. This part of the definition is using a getBoundingBox node and averaging the top left and bottom right points. This point is applied to another wrapper that draws a rectangle with this point as its center point. The final 2 wrappers are identical. These wrappers contain a network that takes a list of numbers and finds the average. Although they are identical now, If I change one of them, the other will not change. If we want to be able to change multiple instances of a Marionette network, we have to first convert the network to a symbol. Let's double-click on one of our average wrappers and select all the nodes inside. We then go to Modify, Create Symbol, and then give our network symbol a name. Let's call it Average Network. When we go to our settings, we want to make sure that Leave Instance in Place is checked and Convert to Group is unchecked. Now that our network is a symbol, let's go to the other average wrapper. Select the network, delete it, and insert the average network symbol. Now, if we edit the symbol, all of the networks will be updated. Not only can we wrap networks, but we can also convert them into plugin objects. If we wrap this network that we made in the last webinar, we can then convert it to a Marionette object. This can be done by right-clicking on the wrapper and selecting Convert to Object node. Now, this network is its own object, but it still has the same parameters in the OIP as the wrapper did. If you change a value, it updates. But with this type of network that has a drawn geometry as its base, you can take this one step further. If we convert the object node back to a wrapper, we can then go into the wrapper and replace the name node that connects the poly to the network with a control geometry node. Once we do this, we select the wrapper and the poly, then right-click on the wrapper and select Convert to Object node. This ties the network directly to the geometry in the drawing space. Now, if we double-click on the Marionette object, we get reshape handles instead of the network. We can still access the network by right-clicking and selecting Edit Script. To create this type of object, you can replace the name node with the control geometry node before or after you convert it, as long as both the geometry and the wrapper are selected when you convert it. When building a network, it is important to remember that if you try to run a network with a control geometry node instead of a name node, it will not work. Control geometry only works when the network is converted along with geometry to a Marionette object. Since we have a little bit of time, I want to go over something that was brought up in the last webinar. In the last webinar, we created a definition where we made a point grid that fit into a polygon. A question was asked after the webinar if instead of putting the point grid inside the polygon, we could find the points of the same grid that were outside the polygon. To do this, we first have to revisit the isInOrOn poly node. This node has two outputs, points and bool, and we learned earlier how a bool output works. This output would be a true or false value for every point that went into the input, depending on whether the point was inside or outside the poly. In the first definition, we used the points output because it gave us only the points that would have had a boolean of true. We could have used the bool output if we also included a filter node. So if we put a filter node into our definition now, we attach the bool output of the isInOrOn poly node to the filter node's bool input, and then we attach the original list of points to the item input of the filter node. The filter node has two outputs, t-values and false values. The filter node takes the input of a list of items and the input of a Boolean list, matches them, and separates them into two lists of true or false values. So if we attach the true values output of the filter node to the locus node, we will get the same result as the points output of the is, in, or on poly node. So since the true values are the points inside the poly, it stands to reason that the false values are the points outside the poly. And if we detach the true values from the locus node and attach the false values, the new network will produce loci outside the poly. So that's all we have for our second Marionette Monday webinar. If we did not answer your question during the webinar, there will be a list of FAQs posted on the forum at forum.vectorworks.net. Join us next time for part 3 of our Marionette Monday webinar series. Thanks!